Hello, I'm Lois Gray, and in this video I'm just going to explain very briefly how to measure gain and phase margins from a Bode plot. So you'll remember that our Bode plot shows us magnitude of gain on the top part and phase change of output versus input on the bottom part. The magnitude is a logarithmic scale, decibels. Hopefully you'll remember that a decibel equals 20 log to the base 10 of our gain. So that's a logarithmic scale. I'm just going to change the pen colour. Okay, and you'll notice along the frequency scale this is also logarithmic. This is the frequency in radians per second. And we use a logarithmic scale so that we can show a wide range of frequencies, from, in this case, from 0.1 radians per second up to 100 radians per second. Okay, and our bottom graph, the x-axis is still logarithmic, but the y-axis is just phase in degrees, so that's a linear axis there. Okay, so let's assume that we have already plotted our Bode plot of our amplifier, and what we found is that we have gain that is rolling off as at high frequencies, which is normal for amplifiers. All amplifiers are designed to do that, and crosses 0 dBs at 10 radians per second. Okay, so that's our amplifier roll-off. So at some point earlier it would have been a high gain amplifier, and now we're getting up to highish frequencies, or higher frequencies we're rolling off. Equally, let's assume that we've plotted the phase for the same amplifier, and we find that the phase has reached minus 180 degrees at 20 radians per second. Okay, so the two important points on our graph are the point at which the gain crosses 0 dBs and the point at which the phase crosses minus 180 degrees. And the reason for that is if we were in a condition where the gain was 0 dBs at the same time as the phase changed at the output by 180 degrees, then essentially we'd be feeding back a signal that would be 180 degrees out of phase with our input signal when our gain was still positive, and we would be adding rather than subtracting the feedback, which would give us a positive feedback condition, which would obviously give us an oscillator or an unstable amplifier. So what we want to do is we want to check that we have enough gain margin and phase margin that even with changes to the gain due to the environment, for instance if the temperature increases, that we're not going to reach the point where the gain is still positive when the phase change at the output is 180 degrees. So the two things we're interested in are this point, and we want to extrapolate that down onto our phase plot, and we also want to extrapolate the minus 180 degree phase point up to our gain plot up here. Okay, so these tell us how much we can shift the gain plot or the phase plot until we get the point of instability, and we want a reasonable phase and gain margin for an amplifier. So in this case, what we're now interested in is where on the gain plot do we get minus 180 degrees phase shift. So that would be this point here. Okay, and reading off the scale here, I see that would be maybe minus 18 degrees or something like that. Sorry, 18 dBs. So I think that point there, which corresponds to this point here, that would give us about minus 18 decibels. So we have a gain of minus 18 dB at the point at which our phase is minus 180. Okay, and then reading off the phase chart, I'll change pen colour again. The point of interest on the phase chart is this point here, and if we read that off on our y-axis scale here, I don't know what that would be, minus 190, minus 120 degrees or something along that line. So let's just say So that's that point there. It's a bit of a guess because the scale is very large. The resolution is very poor on the phase scale, but let's say that's maybe approximately a minus 120 degrees. Okay, so our gain margin is how much we can actually move this graph up until this point here reached the 0 dB point, because if that was shifted up, that 0 dB point would correspond to minus 180 degree phase point. So we can actually shift our graph up by 18 dBs. So we're going to say that our gain margin for this graph, or for this particular amplifier, is 18 dBs, because we can move that point up by that much before we reach the point of instability. Okay, and our phase margin is actually how much we can shift this point down before we reach minus 180. So our phase margin is this distance here. So that's the distance we can shift that point down, the point at which the gain was 0 dBs. And reading from our graph, that's going to be approximately 180 minus 120, so perhaps 60 degrees. That's very much an estimate, because as I say, we can't read very neatly off the scale. If you were doing this for real, I would hope that you would have a more accurate method of reading the scale. So in fact, this is quite a stable amplifier. We would need a gain change of 18 decibels before the amplifier would be unstable, and equally we would need the output to change by another minus 60 degrees before the feedback would become positive at the point where the gain is 0. Okay, thank you for listening. That's all.